Today we're going to start talking about whether a series converges or diverges. We're going to worry about the interval of convergence a little bit later, but right now we're going to have some tests to see if a series converges or diverges. So we begin, it says, by looking at a power series in this form. And it's centered at A. A might be 0. Oftentimes it is. And here's some information that we've had before. There are 3 possibilities when it comes to converging. 3 possibilities that we can say about the convergence of this particular series. First of all, it may converge over an interval. And we saw this where x has got to be between -1 and 1 or something like that. All right? So we've seen where for x values in between 0 and 2, for example. So there might be an interval over which a series converges, and outside of that it doesn't. It might converge for all values of x. If we write enough terms for our polynomial function, and I think we saw that sine x has an interval of convergence from -infinity to infinity. We look at that Maclaurin series we should know at the end of section 11.2. That converged for all values of x, and we haven't seen one of these as of yet. We will sometime soon, but we haven't seen one yet, where it converges only at a particular number and never again. So the radius of convergence would be 0. So again, something that we've talked about before and we just revisit today. Now, the radius of convergence, the interval of convergence, this is the set of all values of x for which the series converges. So it's just sort of defining what an interval of convergence is. And in the rest of this section, and in the next section, we are going to be given ways to determine whether a series converges or diverges. Today we're only going to talk about 2 of them. We'll talk about the nth term test. We're going to talk about the integral test. So that's it for this particular topic. Now, the nth term test is a test which will only test to see if a series diverges. Only good for diverges. So, if we've got a series that looks like this, and the nth term is called a sub n. If the limit as n approaches infinity of a sub n fails to exist or is anything other than 0, then the series is divergent. All right, so let's take a look at this. We are going to take a look at this series in example 1. And we are interested in whether this possibly diverges by the nth term test. So what we're going to do is we're going to take the limit as n approaches infinity of the nth term, and this is the nth term right here. So we go back to the beginning of the year where we were talking about limits, and we've talked about limits approaching infinity and how you can cross off insignificant things. If I cross off this insignificant thing, then this limit is equal to 3. Well, this limit does exist, but it is different than 0. The limit is 3. The limit is not 0. So this series must be divergent because the limit is something other than 0. Now, if the limit is 0, We don't know if it converges or diverges. We can't use the nth term test. We can't say it diverges by the nth term test if the limit is 0, but we also can't say whether or not it converges. We're going to have some other tests that we can take a look at. So, to practice this nth term test, we are going to look at two different things. Towards the end of our packet, on like the second last page of our packet, there's something called Worksheet 4, I think it might be called 10.4, and Worksheet 10.5. And on Worksheet 10.4, I want you to do these two questions. And on 10.5, just a single question. And then in the book, a couple more ways of practicing our nth term test. So that is the homework for nth term, and we'll practice that skill. One other skill we're going to talk about today is the integral test. For the integral test, this goes back to improper integrals that we covered towards the end of chapter 7, which might have been lumped in at the time with chapter 4. Let a sub n be a sequence of positive terms. The integral test can only be used if we have positive terms, can't be an alternating series. Suppose that a sub n is some function that the nth term is found using some function involving n. Then this series and this integral either both converge or both diverge. We have talked about integrals converging and diverging when we talked about improper integrals, and this is certainly improper because one of the limits is infinity or negative infinity. So let's take a look. Use the integral test to decide if the following series converge or diverge. Okay, this series. Well, what I'm going to do is I'm going to take the integral, starting at n being 1, ending when n is infinity. And this, I guess I could rewrite this as n. Oh, you know, let's do this. Let's do this. Let's very temporarily here write this as 1 over n to the 3 halves bn. Now, if I were to turn this into an improper integral, I'd be taking a limit as t approaches infinity, integral from 1 to t of n to the negative 3 halves bn. So let's do that. We're going to take the antiderivative. When we take the antiderivative, we're going to get n to the negative 1/2 divided by negative 1/2, or times negative 2. And that has to be evaluated between 1 and t. If I think of this, you know, I think I just want to clean this up a little bit. I'm going to rewrite this right now. And I'm kind of running out of room, and so I'm going to erase and rewrite that thing. But I'm going to write it as negative 2 over the square root of n. Negative 2 over the square root of n. Now let's put t in here. I'm going to take the limit as t approaches infinity, and I'm going to have negative 2 over the square root of t minus negative 2 over the square root of 1. And that, let's see, this guy here, if t is huge, that's going to be 0-ish. Minus -2 is 2. So I would say that this integral converges, and therefore the series converges. So that series is going to converge. All right. Now this one. We can choose any value of p greater than 1. How about if we choose 2? I'm going to say I've got the integral from 1 to infinity. To save room, I'm not going to do this limit as t approaches infinity. I'm breaking a few rules here, but I want to conserve a little bit of room. And I've got 1 over n squared dn. So again, I'm saying I want p to equal 2 in this case. I chose any number larger than 1. And I'm going to think of this as n to the -2. Now, what's the antiderivative of n to the -2? Well, that would be n to the -1 over -1, or I guess I could think of that as -1 over n. So let's write it that way. -1 over n evaluated between 1 and infinity. Again, if I were doing this as an improper integral, I'd do the limit as t approaches infinity. I'm just saving a little bit of room here. I'll put infinity in here, and I'm going to have -1 over some huge number minus -1 over 1. And I think I see that's going to be 0 minus -1 or 1. So I'm going to say that this series converges as well, because the integral converges, so does the series. So I see if the exponent is 3/2, converges. I see if the exponent is 2, converges. What if I choose a value of p that is less than 1? Let's say p is equal to 1/2. So I'm going to take the integral from 1 to infinity, and I'm going to have 1 over n to the 1/2, which is square root of n. Which is the same as n to the -1/2. So I've chosen a value of p that is less than 1. I'm going to take the integral of that thing. If I take the integral of n to the -1/2, it's going to be n to the 1/2 divided by 1/2, or times 2, evaluated between 1 and infinity. So I put infinity in here, and I've got 2 square roots of infinity minus 2 square roots of 1. Well, now this is such a huge number that when you subtract 2 from it, it's not going to really make much of a dent. And so I would say that this integral diverges. We did not get a definite value. So we see that if p is 1/2, we diverge. Now what if p is equal to 1? If p is equal to 1, I'm going to take the integral from 1 to infinity. And I'm going to have 1 over n to the first. If I take the antiderivative of that, it's going to be natural log of the absolute value of n. Evaluated between 1 and infinity. So we're going to have the natural log of a really huge number minus the natural log of 1. I know the natural log of 1 is 0. So huge minus 0 is huge. And this doesn't have a value, and so therefore it diverges. This integral diverges, and therefore the series that created that integral also diverges. So when p is 1, we diverge. Now, I mentioned this back when we were doing the improper integrals, and I said this is going to come up in our final unit, and here it is. These are called p-series. When you have one, it could be any constant up here. But if we have 1 or any constant divided by n to some exponent, it's the exponent that's going to determine whether or not this converges or diverges. If p is greater than 1, like we saw in these two examples, we're going to find a series that converges. But if p is less than 1, or if p is equal to 1, if p is less than or equal to 1, then the series is going to diverge. Now this thing, if I ever find a use for it, when p equals 1, the series is called a harmonic series. I don't find that to be a real useful piece of information, but if I ever do, I'll let you know. What is useful is the relationship between the exponent on the bottom and whether the series converges or whether the series diverges. Let's take a look at one more example here. Here's the integral test to determine whether this converges or diverges. Well, let's give it a shot. We're going to take the integral from 1 to infinity. 4 over 2 n natural log of n en. And one thing I might be able to do is, could I pull this 4 and this 2 out front? And if I pull the 4 over 2 out front, I would be left with a 1 in here. I'd be pulling a 2 out in front. So I'm hoping you're all okay with that. Now I do have some room here. I can demonstrate this as an improper integral, since it is has an upper limit of infinity. So we'll take the limit as t approaches infinity, and we'll rewrite this as 2 integral 1 to t 1 over n natural log of n d. I'm going to have to write this limit 4 times because this is going to involve a substitution. U is going to equal the natural log of n. And du is going to equal 1 over n dn. And that happens to be exactly what we've got here. 1 over n dn. So now I'm going to write this using my substitution. I'm still taking the limit as t is approaching infinity. I've still got my 2 out front. But now I've got an integral. Let's see. with an n value of 1, I think I've got a 0 here. And with an upper limit of t, I've got natural log of t as my upper limit. I'll replace the 1 over n, dn, with a du, and I will replace natural log of n with a u, which is down on the bottom. And so we'll have, and I better move this over a bit, 1 over n. 1 over u, sorry. Equals, okay, we're going to be taking the limit as t approaches infinity. The antiderivative of this is natural log of the absolute value of u evaluated between 0 and the natural log of t. And so this is going to be equal to the limit as t gets huge. The natural log of the natural log of t, which is a positive term, so I really didn't need those absolute value symbols, minus natural log of 0. Well, this is pretty darn interesting. This right here, the natural log of a huge number, is a huge number, minus the natural log of 0. Well, we can't, it doesn't even exist. You can't have the natural log of 0. I know it does approach negative infinity as we look at that natural log graph. The closer I get to 0, the further down this thing goes. And so we're going to get some number we cannot assign a value to. And so therefore, this particular series, by the integral test, diverges. Now, practice this stuff. Worksheet 10.5, these two questions. And then in the book on page 744, we've got a few more. And please have these completed by the time we get together again.